video module consists of a video program presenting an overview of the topic and a manual containing much more detailed information as well as exercises. To master each topic, you must use the module's components together. View the video program, read the manual, and work the exercises. In our introductory module on wireline logging, GL401, we examined mechanical and electronic equipment that make up a logging unit. We observed how a logging unit was operated at the well site, observed how downhole measurements are made and recorded during logging runs, and we discussed the formation properties that are measured or inferred from logging measurements, such as porosity, phi, permeability, K, and water saturation, S sub W. Now in this video module, we will concentrate primarily on the logging tools themselves, and in particular, we'll examine the principles upon which downhole logging devices operate, as well as the nature of formation information that the different tools provide.
Welcome to GL402, Well Logging Tools and Techniques. In this, the second module of the Wireline Well Logging series, we'll look at electrical, acoustical, and radioactive techniques, as well as naturally occurring events, which when measured, combined, and interpreted, will help us to better understand the downhole environment.
But remember that what we will be measuring, volts or ohms or amplitudes or pulses or time differences, is still only the first step in determining the parameters, such as porosity and saturation, that we'll need to characterize a reservoir or formation. Let's begin.
In this unit, our emphasis is on electrical logging. We will examine several general techniques that have been used through the years to evaluate downhole formations.
These are the spontaneous potential. In the borehole, what can electrical circuits at formation interfaces created by different fluid salinities reveal? And resistivity and induction techniques. What can the electrical properties of the formation tell us?
In electrical logging, several factors control the measured electrical response.
They are water saturation, salinity, porosity, and pore interconnections, sometimes referred to as tortuosity. The first two of these factors are fluid-dependent, while the third is rock-dependent.
Before looking at electrical logging techniques, let's examine how these factors influence our measurements.
Starting off our simple experiment with a sample of distilled water, we pass a constant electrical current from here to here and measure the voltage difference caused by the current flow between here and here. As the salinity of the sample is changed, you can observe a change in the voltage reading. And as we remove some of the water, that is, change the water saturation of our sample, and replace it by another substance, let's say oil, the voltage changes again. Next, if we soak a sponge in our original distilled water sample to simulate a porous formation and again pass an electrical current through the electrodes, we obtain a different voltage reading as compared to the ideal high porosity case. That is, no formation and only fluid. The summation of our results reveals that as salinity increases, current flows between the current electrodes, and there is a potential or voltage drop measured. In logging terms, the conductivity of the sample formation increases, which is the same as a decrease in resistivity. Next, as saturation decreases, the voltage measured increases. And, uniquely in resistivity terms now, so does the resistivity. And finally, as porosity decreases, the voltage increases, and so does the resistivity. It is important to remember that resistivity is measured in ohm meters squared per meter and arises from its definition as the specific resistance through a sample of a certain length and cross-section. Let's now look at two formations that contain the same volume of pore space and are fully saturated with water of the same salinity, but have different types of porosities and permeabilities, and see what we can determine. The path taken by an electrical current across 1 unit length is more tortuous in this rock than in this one. The resistivity R sub O of the rock with a greater amount of tortuosity will be higher than that of the rock with the more direct current pathways. Archie designated this tortuosity effect as formation factor and used F as its symbol. The formation factor, or rock effect, is equal to the resistivity of the 100% water-saturated rock, defined as R sub O, divided by the resistivity of the formation water, defined as R sub W.
Archie established that the formation factor may be mathematically related to porosity by incorporating two constants into his determinations. These constants are generally considered to be related to rock types, pore geometry, and the presence of solid conductors in the clay.
As shown here in this log-log plot, when porosity increases, the formation factor decreases exponentially.
Another Archie equation handles situations in which the saturation of the formation is not 100%.
In these cases, Archie determined that water saturation, S sub W, to the nth root, is equal to the ratio of R sub O to R sub T, where R sub O, you'll recall, is the resistivity of a formation if it were 100% water wet, and R sub T is the actual resistivity of the same formation when water saturation, S sub W, is not 100%. Since N is nearly always equal to 2, it makes S sub W the square root of the ratio of R sub O to R sub T.
This type of relationship means that if we know formation resistivity at 100% water saturation, R sub O, we can estimate formation saturation based on measured R sub T obtained by electrical logs. Let's now have a look at the spontaneous potential and resistivity logging.
The spontaneous potential is the natural electrical potential in the borehole which develops as a result of ion movement between solutions of different salinities. The currents generating this potential are created in the subsurface, primarily in response to two conditions, the liquid-liquid junction effect and the membrane potential effect. The liquid-liquid junction effect, denoted by the symbol E sub Lj, occurs when two solutions of different salinities are in direct contact. As illustrated here, ions move from the more concentrated solution to the more dilute. This condition occurs at the interface of the mud filtrate and the undisturbed formation water. In the case of solutions saturated with sodium chloride, the negative chlorine ions move at a faster rate than the positive sodium ions because of their size difference. The ionic imbalance causes a current flow to develop. The potential is from the fresher mud filtrate to the more saline formation water, but could be reversed if the mud filtrate had higher concentrations than the formation water. The membrane potential develops at shale bed interfaces. The crystalline structures of the clay minerals within the shale act as an ion-selective membrane within which negative chlorine ions are selectively filtered. Positive sodium ions, however, move freely through the clays, resulting in a positive current flow toward the borehole in contact with the shale. Together, these currents at the shale bed boundaries cause a voltage to exist through the drilling mud of the borehole. The voltage measurement is made between an electrode on the downhole tool and a surface electrode, commonly referred to as the SP fish. If a non-conductive, that is, oil-based, drilling mud is used, ion movement cannot develop and no spontaneous potential will be measured.
A log pattern developing over a few hundred feet often permits us to establish a shale baseline and a sand line where thick, clean sandstone occurs. These baselines are used for a number of interpretive purposes, as you will see in the next module, GL403. Now let's examine resistivity logging and the data these techniques provide.
In SP determination, naturally occurring voltages were measured in the borehole. In resistivity logging, however, an electrical current is introduced into the formation. The ease or difficulty with which the current moves through the formation is, as we have seen, dependent on several factors: salinity, saturation, and porosity and pore interconnection. Let's digress with a quick review of the downhole conditions that most affect resistivity measurements and must be compensated for during resistivity logging. These conditions were first introduced in GL401. The different resistivities involved are the resistivity of the drilling mud, denoted by the symbol R sub M, the resistivity of the fluid portion of the mud, R sub MF, the resistivity of the invaded zone, R sub XO, and the true resistivity of the formation, R sub T.
We will start with a simple resistivity measurement to illustrate the basic principle, and we will then be able to apply this understanding to all the other resistivity tools.
In the determination of mud filtrate resistivity, a very simplified and fundamentally understandable method is used. These two end electrodes are the current electrodes, while the two center electrodes are voltage measurement electrodes. When the sample of mud filtrate is introduced and a constant current is passed through the sample from one current electrode to the other, a voltage drop is measured at the measurement electrodes. With two simple equations, we can easily understand the process. This equation is Ohm's law. Voltage, V, is equal to current, I, times resistance, little r. This other equation defines resistivity. Resistivity, big R, is equal to the resistance, little r, times the area A over the length L of the sample being measured. In the case of the mud filtrate measurement, area A and length L are constant and are determined at the moment this mud filtrate cell is manufactured. So if we rearrange the formulas we have just seen, such that we now have a new equation in terms of voltage V, current I, resistivity R, and a geometrical constant L over A, then when a constant current I is introduced into a sample we wish to measure, resistivity is then proportional to voltage, as long as we have adequate knowledge of the geometrical constant. Extending the mud filtrate measurement principle to the borehole, we can define a constant current source, I, with its other electrode on the surface and a voltage measurement pair of electrodes, one in the borehole and one on the surface. The simplest resistivity tools are set up to introduce a circuit between the borehole and the surface. Point A is the source electrode, and point B is the current return in this illustration. The potential drop is then measured between the borehole and the surface. Points M on the tool and N at the surface in this illustration. Knowledge of the geometry of the system permits conversion of a voltage drop into resistivity.
But what about the geometry of this system? In our simplified mud filtrate measurement example, we simply stated the L over A factor as a constant. In the case of this tool, the situation is slightly more complex.
Mathematically, the equation of interest still is the voltage V equals current I times resistivity R times the geometrical constant L over A. Now we need to focus on the L over A factor, and specifically make some assumptions on the path the current will take. Our assumption is that the current radiates spherically out from the source in the borehole, equally in all directions, and our intent is to measure the voltage here at the measure electrode and compare it to here at the surface. In order to measure the voltage change, we will have to rely on integral calculus to help us obtain the voltage change with respect to distance from the current source. This change is referred to as dV over dr, where little r now signifies radius and not resistance.
Since the area of a sphere is 4 pi r squared, we substitute this for area A and substitute little r for the length L. Rearranging our terms and integrating dV over dr will result in V equals IR over 4 pi AM, where AM is the distance between downhole current and voltage electrodes. Therefore, in our simple model, the geometry constant of our equation is tool-dependent and is not dependent on downhole factors. But the basis of our result hinges on the acceptance of the spherical current radiation model.
In general, current flow can be characterized as flowing away from the source through the borehole and rock of semi-uniform resistivity and being collected by the return electrode.
This means that the resistivity measured by a logging tool primarily reflects the combined resistivity of the mud, R sub M, the resistivity of the invaded zone, R sub XO, and the resistivity of the rock, R sub t, in the near vicinity of the electrical source. In the configuration we examined, the resistivity logging tool is called a normal device, with a spacing represented by the distance from electrode A to electrode M. By rearranging the system such that point N is now downhole, the logging tool designation becomes a lateral device, with spacing represented by the distance between the current source electrode A and imaginary point O, representing the midpoint of electrodes M and N.
As you have seen, spacing is an important factor in tool design because it determines the effective depth of investigation into a formation. Very close spacing may measure only slightly into the invaded zone, while a broader spacing gives measurements of greater investigation and can measure resistivity of the undisturbed formation.
An example of the spacing effect on a logging tool is shown by this micro-resistivity device called a microlog. It has one source electrode, indicated by A, and two voltage measuring electrodes, M sub 1 and M sub 2. The spacing of the source and the measure electrodes is very close, approximately 1 inch. Therefore, the depth of investigation is shallow, only a few inches maximum.
There is a common difficulty encountered by simple normal and lateral resistivity devices suspended in the borehole.
Very conductive mud can short-circuit the logging current such that the resistivity of the formation is not sufficiently represented.
Modern electrical logging devices commonly avoid the problems associated with very conductive muds by focusing the electrical current laterally into the formation. This lateral focusing is done with currents generated by the nearby electrodes on the tool.
In one focusing method, electrodes are placed above and below the source electrode. These added electrodes carry currents of the same polarity and approximate strength as the source electrode. The result is that the measure current is prevented from moving up or down the borehole through the mud by these guard currents. Consequently, the measure current must take a pathway directly into the formation. The process is based on the fact that current paths do not cross.
Let's start off with the point source electrode and see how resistivity is measured on such focused tools.
Several electrodes will be used. The source electrode is in the center of the assembly, designated A sub O. Focusing or guard electrodes, designated A sub 1 and A sub 2, are placed above and below the source electrode. 4 sensing electrodes, M sub 1, M sub 2, M sub 1 prime and M sub 2 prime, are placed above and below the source electrode, between the current electrode A sub O and the guard electrodes A sub 1 and A sub 2. To carry out the logging process, a constant current is applied to the current source electrode A sub O. At the same time, current of the same polarity is sent through the 2 guard electrodes, A sub 1 and A sub 2, to focus the constant current. The current from the guard electrodes is automatically adjusted during the logging process, such that the voltage between the pairs of sensing, or M electrodes, is maintained at 0.
The result is a sheet of electrical current radiating from the current source electrode that has approximately the same thickness as that between the midpoint of the sensing electrodes.
For a known amount of current flowing into the formation, the measured potential between the M electrodes and an electrode considered to be at a 0 voltage or 0 potential reflects formation resistivity. These 0 potential electrodes may be on the surface or downhole, but generally are suitably distant from the other electrodes. If we were to place a second set of guard electrodes closer to the source, then the depth of investigation would be shorter for this new array.
In turn, this dual depth of investigation logging, with further signal processing, can give us a plot of undisturbed formation resistivity and flushed and/or transition zone resistivity from a single logging pass. Let's look at typical resistivity curves measured by a dual system such as this.
Typically, we can obtain a curve measuring deep resistivity, a curve measuring shallow resistivity, and a curve measuring very shallow resistivities in the flushed zone just behind the mud cake. To determine resistivities and invasion diameter, we start with the example we saw earlier. The voltage drop measured by a deep resistivity tool measures the voltage drop caused by mud resistivity plus invaded zone resistivity plus undisturbed zone resistivity. Now, if we remember that voltage is equal to current times resistivity times a tool constant geometry, or V equals I times R times K, then we can state that the voltage measured by a focused deep reading device is equal to the current, I, times the resistivity of the mud, R sub M, adjusted for the hole diameter, plus the resistivity of the invaded zone, R sub XO, adjusted for the invasion diameter, D sub I, plus the formation resistivity, R sub T, times the contrast between the formation and the invasion zone resistivity, all times the tool constant.
In this situation, there are three unknowns: the resistivity of the undisturbed formation, the resistivity of the invaded zone, and the diameter of the invaded zone. These three unknowns can be determined by using three equations implementing three resistivity measurements.
The mathematics involved in making final determination of resistivity are complex and include the use of a pseudo-geometrical factor, J.
In addition, resistivity data generally require correction for borehole effects. For this, correction charts are provided by the various logging companies. Final values for the three unknowns are read from charts usually referred to as tornado charts, and these determinations give resistivity data that can be compared from interval to interval and hole to hole, as long as mud filtrate invasion diameters are within the tolerances of the charts. But a word of caution: log analysis may require the use of additional investigation for localized subsurface effects.
Near thick resistive beds like salt and anhydrite, currents may be distorted, and some logging devices may produce and record anomalous resistivity measurements.
Correction for these conditions may be necessary. The influence of these anomalous effects is summarized in your manual. Before discussing induction resistivity devices, let's quickly look at the normal calibration procedures of electrical resistivity tools.
Since these tools measure voltage changes caused by varying resistivities, it is relatively easy to reproduce a unique voltage with precision resistors and a stable current source in the tool. In fact, all these tools have built-in calibration resistors, which are used by the engineer to determine a low-end and a high-end calibration point by which the logging system response is then determined. Once calibrated, the tool system will respond to ranges of resistivities encountered in logging.
Now, induction resistivity tools find their most effective application in holes where non-conductive fluids, such as oil-based muds, are used during drilling. Induction devices can evaluate the formation electrical properties even when no electrical current can be transmitted from the tool through the mud to the formation, a condition essential in resistivity logging. The induction tool responds to the conductivity, the inverse of resistivity of the formation in the vicinity of the borehole. Let's see how the tool functions.
In the borehole, a transmitter, energized with a constant alternating current, induces a secondary current in the formation concentrically around the borehole. This induced current moves in ground loops about the borehole and logging tool. This secondary current, in turn, induces a response in the tool's receiver coils.
In actual tools, service companies have added extra transmitter and receiver coils to the idealized two-coil model as a means of achieving focus on certain regions of the formation and to minimize the response from the near wellbore area and from shoulder beds. Since horizontal and vertical focusing of the measurements is possible, it follows that, like electrical resistivity tools, induction devices can be configured for dual functions with multiple transmitter and receiver coils.
With more than one measurement being made by a single tool, we can solve for more than one unknown, as we did with multiple electrical resistivity devices. Again, we are able to determine and solve for the formation resistivity, R sub T, the diameter of invasion, D sub I, and the flushed zone resistivity, R sub XO. The magnitude of the induced secondary current and the response measured by the tool depend on the conductivity of the formation. The higher the conductivity, the larger will be the secondary current and measured response. The direct measurement made by the induction tool, then, is one of conductivity.
This measurement is expressed in millimos per meter and in resistivity units, ohms meter squared per meter, to match the presentations on resistivity logs.
As with electrical resistivity devices, corrections for downhole environmental effects and borehole conditions are necessary. One correction is for skin effect. This term is used for interference and secondary currents that develop among the infinite number of ground loops within the induced magnetic field. The net effect is to reduce the returning current signal received by the tool.
The magnitude of the loss plotted here shows that as the conductivity of a formation increases, the skin effect becomes more pronounced. Consequently, the returning current signal at the tool will be progressively diminished with increasing formation conductivity. However, compensation for skin effect losses is now automatic.
Another correction for induction tools is for bed thickness, since deep horizontal investigation leads to poor vertical bed resolution.
The corrections for bed thickness are carried out with charts. By plotting bed thickness against measured resistivity, an improved resistivity of the center of the bed is determined. Other corrections for induction logging include hole signal and effects of drilling filtrate invasion.
Like most logging tools, the induction has a two-point calibration.
Since the measurement is one of conductivity, the tool is first placed in a zero conductivity environment and should measure zero conductivity or infinite resistivity. Now, when an artificial formation of known conductivity is introduced and placed about the tool sensitivity can be adjusted to measure its value. After these two endpoint measurements are made, the tool response will be able to reproduce conductivity and inversely resistivity measurements found in most formations. Since this procedure is somewhat cumbersome at the well site, calibration resistors in the tool reproduce the values obtained during this periodic check. As with all logs, calibrations are performed before and after the survey and added along with the master calibration results to the log.
This concludes Unit 1 in our examination of resistivity devices. Take time now to complete the exercises in your manual that accompany this unit.
You'll recall from Unit 1 that fluid salinities, saturation, porosity, and pore interconnection have a considerable bearing on log data obtained by electrical tools. In Unit 2, you'll find that properties such as rock elasticity, gamma-ray absorption, and hydrogen ion content play an equally important role in evaluating subsurface porosity.
This logging device is an acoustic tool. It transmits acoustic energy into the formation, traveling as elastic waves from the point of origin at the transmitter to the point of measurement at the receiver. Before getting into the mechanics of acoustic logging, let's look at some fundamentals of elastic wave travel.
In the subsurface, acoustical energy is transmitted through rock in several forms, two of which are a compressional wave with elastic deformation in the direction of propagation, and a shear wave with elastic deformation transverse to the direction of propagation. The compressional wave travels through both solids and fluids, such as the mud of the borehole, but travels faster in solids than in liquids.
Therefore, a high porosity formation with liquid-filled pore space has a higher compressional travel time than a compressional wave traveling through non-porous rock. This is the fundamental basis of porosity determination utilizing acoustical energy.
The shear wave is transmitted effectively only in solids where lateral distortion can be perpetuated. Consequently, the shear wave is not transmitted effectively by drilling mud. It can, however, be measured. The compression, or C wave, moves faster than the shear, or S wave, in any single solid medium, rock in this case. Consequently, the compression wave always arrives at a distant point ahead of its companion shear wave, and is the wave used in conventional sonic logging as the measure of acoustic travel time, delta T, or script T, from source to receiver. The time period from transmission to detection of the first arrival of the compressional wave is the measurement made in conventional acoustic sonic logging. When an interface between a solid and a fluid is present, as between the mud and rock at the bore wall, two additional acoustical waves develop. These are a Rayleigh wave, which travels along the rock of the bore wall in an elliptical retrograde motion, and a Stoneleigh wave, which travels along the rock-mud interface, also with an elliptical retrograde motion. The Stoneleigh wave, or tube wave as it is sometimes called, is a result of interaction between the shear wave in the rock and the compression wave in the mud. The acoustical signal arriving at a distant receiver is a composite of all wave types, as shown here. The first arriving compression wave, the second arriving shear wave, next the Rayleigh wave, and finally the Stoneleigh wave.
Acoustic logging operation follows a certain methodology. First, a transmitter initiates the compressional wave that passes through the mud into the bore wall. The wavefront encounters the bore wall at a critical refraction angle, moves along the wall, and sends more compressional waves back into the mud. This returning wave is measured by a receiver, and the travel time from source to receiver is determined.
Typically, receivers are in pairs, so that the time taken by the acoustical wave to pass through the mud from the source to the receivers is effectively subtracted out by determining the arrival time difference between the two receivers.
As we have seen with many logging devices, when the spacing between the source and the receiver is increased, the depth of investigation is increased. Using this principle, long-spaced acoustic devices obtain travel time measurements for undamaged and unaltered formation beyond the bore wall.
The capability exists to record waveforms and identify the arrivals of compression, shear, and Stoneleigh waves, and to measure their transit times. These data can be stacked together and give an interpretable impression of bore wall conditions. In addition, manipulation makes it possible to measure beyond casing with the acoustic sonic technique. For example, this log uses acoustic energy to determine the effectiveness of a casing bond.
There are other general uses of acoustic tools, such as calibrating seismic velocity surveys, fracture detection, waveform analysis, overpressure determination, and formation analysis. You should also learn from the manual the limitations of acoustic devices and the problems that may develop with signal detection and unwanted noise detection.
Before moving on, let's understand that acoustical sonic devices are time measurements between events. These devices do not have calibrations like other logging tools, but engineers frequently make a record of stable, repeatable events, such as uncemented casing that reads a constant value.
A variety of devices measure radioactive properties. This gamma ray tool is relatively simple and measures the complete spectrum of natural radioactivity emitted from the formation.
This larger device, called a formation density tool, has a gamma ray source and companion detectors. It measures the absorption effect of different rocks and fluids near the borehole as gamma rays pass through them. From these gamma ray measurements, calculations of the bulk density of the formation can be made. A density tool may also be configured to selectively measure gamma ray spectra in different energy ranges so that lithology can be interpreted. This device is called a lithodensity tool.
This other device, typically called a neutron tool, has a neutron source and detectors from which porosity determinations are made. A nice feature about most of these devices is that they can investigate beyond steel casing, a capability electrical logging tools do not have. Let's begin with a simple gamma ray tool and its modern specifications.
The conventional gamma ray tool consists of a Geiger-Müller counter or a more sensitive sodium iodide scintillation detector in crystal, which counts natural gamma ray emissions for fixed intervals of time. These emissions originate through the natural decay of radioactive elements in the formation surrounding the borehole. The radioactive elements are due primarily to uranium, thorium, and potassium. As each of these radioactive elements disintegrates toward its end products, it gives off a spectrum of gamma rays of specific wavelengths. As shown here, uranium and thorium have characteristic spectra of wavelengths, and potassium has a single emission wavelength. The total count rate per time interval is plotted in API units, which have been established by the industry. The greater the count rate, the greater the API reading.
This calibration pit has been constructed at the University of Houston. In this pit, cement containing small amounts of disseminated uranium, thorium, and potassium salts has been sandwiched between two layers of untreated Portland cement. The API standard defines the difference in gamma ray activity between the untreated zone and the treated radioactive cement zone as being 200 API units.
A tool is calibrated by placing it in the pit and then equating the difference in readings to 200 API units. Since all tools cannot be run routinely through the test pit, field calibration sources produce known gamma ray emission rates. These are used to confirm that a tool is properly calibrated. Two common uses of simple gamma ray devices are correlation of stratigraphic units and estimation of shale content. Remember the gamma ray spectra for uranium, thorium, and potassium that we showed earlier. Sophisticated gamma ray devices add another general use to gamma ray logging. They measure the energy level of the natural gamma ray spectrum coming from the formation, and can determine what percentage of the total energy spectrum can be attributed to either uranium, thorium, or potassium. Results of gamma ray spectroscopy are presented in this format. In the left column are a total gamma ray curve and a uranium-free curve. On the right are curves of uranium concentration, thorium concentration, and potassium concentration. Before discussing other radioactive logging tools, remember that gamma ray logging can be adversely affected by downhole conditions. A change in mud weight, hole size, casing in the hole, cement thickness, or the position of the device in the hole, centered, eccentered, or tilted, will affect gamma ray count. Correction charts are available to compensate for the effect of downhole variables.
In our introduction of radioactive tools, we briefly discussed formation density devices. Before continuing, recall from basic physics that when material type is known and its density can be measured, estimates about its porosity can easily be made.
The formation density tool radiates the formation with gamma rays from this source area and measures gamma rays returning at these detectors. By introducing a known amount of radioactive energy into the formation and monitoring its loss while in transit, a good approximation of rock density can be made. Here is how the formation density tool works. Gamma rays are emitted continuously from the source. They pass through the mud cake into the rock, where they are scattered or absorbed. Some return back through the mud cake to the detectors to be counted.
In the formation density tool, source detector spacings are so close that the device evaluates the invaded zone close to the bore wall.
The loss of gamma ray energy that occurs in transit from source to detector is caused by three effects. The first is Compton scattering, which occurs when a gamma ray collides with an electron and loses some of its energy as it knocks an electron from its orbit. The second, photoelectric effect, which occurs when a gamma ray collides with an electron and loses all its energy as it knocks the electron from its orbit. The third reaction, pair production, occurs with gamma ray bombardment. However, the gamma ray source used in a formation density tool is of relatively low energy and below the threshold of pair production. Consequently, we'll ignore pair production and concentrate on the other two effects. The net effect of these two interactions is that the number of gamma rays penetrating a substance decreases as its density increases. A returning high gamma ray count indicates low density rock. A low gamma ray count indicates high density.
What is really measured by the tool, however, is electron density, characteristically denoted by rho sub E. Let's see how the conversion from measured electron density to calculated bulk density is made.
The number of electrons in any atom determines how effectively it will deflect and alter gamma rays. The number of electrons is denoted by an atom's atomic number, Z. The number of protons and neutrons of an atom determines its atomic weight, A, and therefore its contribution to the density of any molecules in which it occurs. The general relationship between bulk density and electron density is as shown here. For most common elements, the conversion ratio, 2Z over A, will be approximately 1, and the electron density will read close to true bulk density.
As we said earlier, bulk density can be taken almost directly from measured electron density for atoms like oxygen and carbon, which have conversion ratios of approximately 1.
For example, limestone, or its mineral constituent, calcite, CaCO3, has a conversion ratio of 0.9991. This represents the sum of 2 times the total number of electrons in the molecule divided by the molecular weight. Water, in contrast, has a higher conversion ratio of 1.1101 because of the presence of 2 hydrogen atoms in each water molecule.
These varying values require that a formation density tool be calibrated to a standard. The industry standard in this case is pure limestone saturated with water. The tool is calibrated to read an electron density of 1.11 in water and of 2.71 in pure limestone. This represents their true density based on calculated molecular weight.
When so calibrated, measured apparent densities of different minerals will read very close to their true densities. For example, the true density of quartz, or pure sandstone, is 2.654. Apparent density measured by gamma radiation will read 2.648.
The primary use of bulk density is to determine porosity of the rock. Porosity is calculated from the measured density in this general manner. If we know the density of a rock type with no porosity, for example 2.71 for limestone, and we know the density of pure formation water, then the measured density will represent some proportion of each.
Corrections must be made for the effects of mudcake and bore wall rugosity on tool position and gamma ray absorption. This is done by evaluating the differences in response between the close-space detector, which senses primarily the bulk densities of the mudcake and bore wall irregularities, and the long-space detector, which senses both of these, plus the bulk density of the flushed formation.
Before we leave gamma ray density tools, we need to examine their capabilities when configured for lithology density measurement. In this case, not only is the loss of gamma radiation through Compton scattering measured, but also the spectrum of gamma rays that results from photoelectric absorption.
The effect of Compton scattering, as we saw in the calculation of conversion ratio, is directly dependent on the number of electrons present in the molecule. Photoelectric absorption is related to the atomic number Z of the elements encountered. Therefore, measurement of gamma ray energy and photoelectric range can lead to lithology identification.
As discussed in your manual, different lithologies have different photoelectric absorptions, which are independent of bulk density.
As you can see here, even though different rock types can have similar bulk densities, lithology differences generally result in diagnostically different photoelectric factors.
Before leaving density logging, let's quickly discuss the calibration method.
Service companies utilize an aluminum block for periodic master calibrations. The tool is placed in the block and a reading is taken. Certain count rates are recorded and can be reproduced at the well site. Further tests can be made by the insertion of different types of materials to alter the count rates. At the well site, field calibrators are utilized to make a check of these tools prior to logging. As usual, these records become a permanent part of the survey.
Let's now look at the remaining common logging technique that uses radioactivity to evaluate conditions in the subsurface. With this particular neutron logging tool, the radioactive source is here, and the detectors are here and here. The tool is pressed against the wall of the borehole and mudcake by a spring.
In greater detail, a neutron source emits high-energy neutrons into the formation. The individual neutrons collide with nuclei of atoms in the formation. Each collision reduces the energy level of the impacting neutron until it reaches an intermediate energy level. At this energy state, a neutron is called an epithermal neutron. As epithermal neutrons collide with more nuclei, they lose additional energy until they come into general equilibrium with the surrounding nuclei. At this level, they are called thermal neutrons. Most neutron tools detect returning thermal neutrons.
Now, because of size similarities, the common chemical element that is by far the most effective at degrading neutrons from high energy to epithermal to thermal levels is hydrogen. When neutrons reach the low energy thermal equilibrium level, they are very susceptible to capture by nuclei in the formation. When neutron capture occurs, a gamma ray is released. This capture gamma ray is detected and is proportional to the amount of hydrogen in the formation.
When the tool is in the hole, high-energy neutrons penetrate the mud cake and formation as they start their degradation through epithermal to thermal neutrons. As they move away from the source, a thermal neutron flux, or gradient, is established that depends upon the collision rate between the formation nuclei and the neutrons. The flux rate declines with distance from source, and at a different rate or slope depending upon porosity. This relationship of neutron flux to porosity is mostly the result of hydrogen in the water molecules filling pore spaces. High initial thermal flux rate and rapid decline is to be expected with high porosity because of the abundance of water. The inverse, low initial thermal flux rate and slow decline, is to be expected with low porosity.
A series of single flux measurements taken by a logging device will not accurately determine porosity because of variables like mud cake thickness, mud weight, mud composition, and bore wall irregularities. But the general form of the curve remains the same even though its position on the neutron flux graph changes.
Therefore, measurement of the slope of the curve at known distances from the source can determine which porosity curve is represented. Consequently, in modern tools, flux rate is measured by two detectors to compensate for borehole conditions. By plotting these two flux values, a slope is determined that is relatively independent of borehole variables. The flux rate measured at two detectors is proportional to porosity.
Corrections must be made when gas is present in the pore spaces because of the lower density of hydrogen atoms. Likewise, shale with water in its structure results in a high thermal flux rate and a corresponding high porosity value.
In general, neutron tools need to be corrected for environmental effects, such as hole size and salinity. Chlorine, too, has a very efficient thermal neutron capture capability, which results in false high porosity measurements. Therefore, the presence of chlorine requires such corrections. Calibration of neutron tools is performed in water-filled tanks. The ratio of detector count rates can be computed and recorded for later well site sensitivity adjustment. At the well site, a field calibrator is utilized to reproduce the periodic monthly calibration value. As with all other tools we've discussed, these calibration records become a permanent part of the survey.
We shall now conclude Unit 2 by looking briefly at a tool that uses high-frequency electromagnetic energy.
This pad is part of a dielectric or electromagnetic propagation device. It should be classified as an electrical device. However, some strong analogies between electromagnetic waves and acoustical waves are evident. The tool consists of two microwave transmitters and two receivers. Spacing is close to allow examination of the invaded zone directly behind the mud cake. Borehole compensation is accomplished by sending electromagnetic waves alternately from each transmitter, with the drop in wave energy and frequency measured between the two receivers. Three general determinations are made: phase shift of the electromagnetic wave, propagation time of the wave, and attenuation of the wave. As microwave energy of a fixed intensity and wavelength moves through the formation, two marked changes occur. The waves lose some of their amplitude, and the wavelength increases.
The cause of these shifts is due to the dielectric permittivity of the rock and the fluids through which the electromagnetic energy propagates. The dielectric effect of rock, oil, and gas is quite low, and the tool responds by a moderate decline in electromagnetic amplitude with a relatively high propagation time.
However, the presence of water in pore space results in a high dielectric permittivity, which is reflected in an increase in propagation time. A quick application of this result is to calculate a porosity curve based on attenuation and transit time, and then compare it with other porosity curves.
This concludes Unit 2 and Module GL402. You have seen how some acoustic, radioactive, and dielectric devices operate, and how they are dependent on subsurface conditions like porosity and fluid saturation. In our next module, GL403, Formation Evaluation, you'll learn how to relate tool measurements to subsurface conditions.